Welcome, everyone. Today we'll be exploring a fundamental concept in modern processor design, pipelining in computer architecture. We'll go through its working mechanism, types of hazards, and performance benefits, supported by real-world examples. Pipelining is a powerful technique used to enhance instruction throughput in CPUs. Instead of processing one instruction at a time, pipelining overlaps different phases of instruction execution. This makes CPUs significantly faster and more efficient. Imagine an assembly line in a factory. Each stage performs a task and passes the product on. Similarly, in pipelining, each stage completes a part of an instruction, such as fetching, decoding, executing, etc. Multiple instructions can be processed simultaneously, each at a different stage. A classic 5-stage pipeline includes instruction fetch, if, instruction decode, ID, execute, EX, memory access, MEM, write back, WB. Each instruction moves through these stages, with different instructions occupying different stages simultaneously. Pipelining aims to improve performance. Ideally, a pipeline with n stages can improve throughput by a factor of n. However, due to various hazards and dependencies, the actual performance often falls short of this ideal. Pipeline hazards disrupt the smooth execution of instructions. There are three main types: structural hazards, data hazards, control hazards. Each type affects performance differently and needs specific handling techniques. Structural hazards occur when hardware resources are not sufficient to handle overlapping instructions. For example, if two instructions need the ALU at the same time, a conflict occurs, leading to stalls. Data hazards arise when instructions are data-dependent. For example, if one instruction needs the result of a previous instruction that hasn't completed yet. These are further categorized into raw, read after write; war, write after read; WAW, write after write. Control hazards are caused by branch instructions, like jumps or if-else statements. When the outcome of a branch isn't known immediately, the processor might fetch the wrong instruction, wasting cycles. Several techniques exist. Forwarding sends results directly from one pipeline stage to another without waiting. Stalling introduces delays to wait for data readiness. Compiler techniques like instruction reordering can reduce hazards at compile time. Control hazards are handled using branch prediction, where the processor guesses the outcome. Delayed branching, where certain instructions are always executed regardless of branch outcome. Branch target buffers, BTB, to store past outcomes. Pipeline hazards disrupt the smooth execution of instructions. There are three main types: structural hazards, data hazards. Forwarding solves data hazards by routing data directly from one pipeline stage to another, eliminating the need to wait for write back. This significantly improves performance without adding delays. Branch prediction tries to guess the outcome of a conditional branch. If guessed correctly, it avoids stalls. Prediction can be static, always taken or not taken, or dynamic, based on history. Several techniques exist. Forwarding sends results directly from one pipeline stage to another without waiting. Stalling introduces delays to wait for data readiness. Compiler techniques like instruction superscalar processors use multiple pipelines to fetch and execute more than one instruction per clock cycle. This enables higher instruction throughput and better CPU performance. Out-of-order execution allows instructions to execute as soon as operands are available, regardless of their original order. This maximizes the usage of available resources and avoids unnecessary stalls. Pipeline depth refers to the number of stages. Deeper pipelines can potentially increase clock speed but also increase latency and control complexity. Balance is key. Key advantages include increased throughput, efficient resource utilization, shorter cycle time. These benefits make pipelining integral to modern processors. However, pipelining isn't without drawbacks: complex hazard control, increased design complexity, diminishing returns beyond a certain number of stages. Examples of pipelined processors: Intel Pentium uses a classic 5-stage pipeline. ARM Cortex-A8 has 13 stages for higher throughput. Modern CPUs often use 14-20+ stages with advanced hazard handling. RISC architectures, with simpler instructions, are easier to pipeline efficiently. CISC architectures involve complex decoding, making pipelining more challenging. This is one reason why RISC designs are popular in mobile and embedded systems. Data hazards arise when instructions are data-dependent. For example, if one instruction needs the result of a previous instruction that hasn't completed yet. These are further categorized into raw, read after write. Common metrics: CPI, cycles per instruction, lower is better. Throughput, instructions per second. Latency, time to complete a single instruction. Pipelining aims to reduce CPI and increase throughput. To summarize, pipelining increases instruction throughput. It involves dividing instruction execution into multiple stages. Hazards must be effectively handled. It's a foundational concept in all modern processors. That brings us to the end of the presentation. Thank you for your attention. I'd be happy to take any questions you might have.